Now for the fun part, analyzing numerical data. The first thing we want to do is come up with some data to analyze. Let's use our favorite data set, the iris data. Specifically, let's take a look at iris setosa sepal widths. Let's say we know that the population mean mu equals 3.43 centimeters and sigma equals 0.38. We take a sample of 5 individuals that have sepal widths of 4.2, 4.4, 3.8, 3.7, and 3.6 centimeters. The question is now, is this sample unique or unusual? First off, we need to calculate our sample estimates. First, we're going to take the sample mean, which is x bar. We already know how to calculate that, and we get 3.94 centimeters. We also calculate the sample standard deviation, which is s, which is the square root of s squared, and we get 0.34. As a reminder, mu, the population mean, equals 3.43 centimeters, and sigma, or the population standard deviation, equals 0.38. We can z-transform that sample mean using the equation z equals x bar minus mu over sigma divided by the square root of n. However, in many cases, we don't know what sigma is. Let's assume that we don't know the sigma for the iris setosa sepal widths. However, we can estimate s, the sample standard deviation, and use that as an estimate for sigma, the population standard deviation. In this case, we cannot use normal distribution. Instead, we use the t-distribution. The t-distribution looks at a whole lot like the normal distribution, but has longer tails. These longer tails reflect the uncertainty in the population standard deviation. We parameterize t with degrees of freedom, df. We can use t to calculate confidence intervals. To estimate the 1 minus alpha confidence interval, we calculate x bar plus or minus the standard error of x bar times t at a particular alpha that's two-tailed with the degrees of freedom that we calculate. A 95% confidence interval equals x bar plus or minus standard error of x bar times t with an alpha of 0.05. 99% confidence interval is the same thing, but t will be an alpha of 0.01. When degrees of freedom are large, the t distribution approaches that of the standard normal.